back from break. I hope everyone had a good break and safe break, and that you remember to use sunscreen. We're going to start today with a demo. Okay, I wasn't very nervous, and the principle that is saving my life is conservation of energy. Okay, that's what we're going to talk about today. Call this the bowling ball of death, and it didn't look like I was coming that close to death. Back in the old building, and when we taught in Reed, we had a little eye hook up in the middle of the ceiling, and we would bring the bowling ball clear across the room and stand up against a brick wall, and that bowling ball would swing across the room and come right back up and touch the nose. And when we built this new building, all of us came in and looked for a place where we could put that eye bolt, and the people in the Burns Telecommunications Center, no way you're going to swing a bowling ball near that great big beautiful screen. So they nixed it. So Jerry came up with this alternative. We are very appreciative of his work there. Now, we're going to be talking about conservation of energy today. And this is a topic that I know you covered in the 4th grade, and then you covered it again in the 6th grade, and then again in the 8th grade. It's a very popular topic. We're going to hopefully go deeper and give you a better understanding of this idea of energy. Whenever we start a new topic, we have fairly basic homework problems to begin with. These are fairly basic, and I'm going to show you how to do problem 4 before the end of today's lecture. Now, that demo, as good as it is, has some flaws that we'll talk about in a little bit. Let me show you another demo that was done when I was younger. I was a cute kid, huh?
What type of energy does the ball Earth system have just before release? What kind of energy is largest at the lowest point of the arc? Why doesn't the ball strike the boy upon return?
Yeah, why?
Why was the concrete block wall knocked down?
All good questions. Now, when we did it over in Reed Hall, it was departmental policy that you always had to have your head up against the brick wall before you started the demo. And you'll notice that kid had his head firmly up against the brick wall when he was doing it. Why is that important?
So you don't sway forward?
Yeah, you know where your head is if it's up against the wall. Okay, it turns out that this became departmental policy after an accident. The gentleman who had this job before me, Denny Lee, this is not how he died. He's still alive, actually. But he was just away from the wall, and he started it, and then he leaned forward a little bit as he was talking. And it came back, hit his mouth, there was blood, there was stitches. It was the demo you always dreamed of. And that's when we came out with a new policy that said, thou must have your head against the brick wall. let's talk about this idea that you've covered before in all of those previous classes. Turn to your neighbor and answer this question. What is energy? What exactly is it? Okay. My experience has been that if I ask 5 of you to share your definition, I'll get 5 very different definitions. Many of you have learned definitions over the years, like the capacity to do work, or many of these definitions are very mathematical. But I think the best definition that I can come up with at a gut level is energy is the capacity to mess stuff up. It's a capacity to break things, to do damage. Okay, if something has a capacity to ruin your whole day, that's energy. Okay? Now, what types of energy have you heard of? Raise your hand and share with the group here. Kinetic energy, energy of motion, yes sir. Okay, kinetic? Potential. There's different kinds of potential. There's gravitational, there's chemical. Okay. And thermal energy. That was what you were going to say? You're supposed to say jinx then. What?
Gives energy. Gives energy.
Gives energy. Okay, a chemist in the room. Gives free energy. Okay. There's all sorts of different kinds of energy. We've got light is energy. We have energy of deformation that we'll talk about when we get into collisions. There's all sorts of types of energy. We are going to restrict our discussion in this class to 3 different kinds of energy. And today we're only going to talk about 2 of those kinds. We're going to talk about kinetic energy associated with motion and gravitational potential energy. Okay? Now, here's the thing. I have tried very, very hard throughout this semester, and indeed throughout my life, to never say, trust me, take my word for it, because I said so. That's not the way you should teach physics. That's what the tutorials are all about. You're building the physics from the ground up so that you own it. I would hate for you to go to a party 10 years from now, and at that party, for one reason or another, they're talking about physics. I mean, it can't be that good of a party. And suddenly they come up with a question, and you've got the answer. They, whoa, how did you know that? Oh, Greg Francis told me. I will feel like a failure if that comes out of your mouth. Greg Francis told me. It should belong to you. Now, here's where I apologize. Today, I'm going to ask you to trust me. And that's not what I've always done. It turns out that in 1998, my good friend Jeff Adams and I were team teaching this course. And it was one of the most wonderful learning experiences for, well, both of us. We had both taught the physics for a long time. We both had our own way of doing it. And so when we came together to create lectures, it was a fight every time. And that fight would go on for days. And the biggest fight we ever had was over this lecture. I wanted to develop the ideas from the ground up and build up the equations and let you see where they came from. Jeff wanted to just give you the equations and show you how to use them. And that's wrong. That's sick and wrong. And I wanted to burn him at the stake as a heretic. But then he asked me a question. He said, Greg, how's your approach working? I said, oh, really bad. I mean, the students fall asleep. They don't really pay attention. It's awful. He says, okay, let's try it my way. So we tried it his way. I've never gone back. Now, folks, I don't feel comfortable doing this, but I think it's best. I'm going to ask you to trust me, but only till Friday. trust and verify. Okay? Now, Friday I'm going to show you where these equations come from. But today I'm just going to give them to you. I'm going to ask you to believe me. And then I'm going to show you how they are so powerful in helping us solve problems. Now, we're going to start with a very simple example. The example is just dropping a ball and letting it speed up. Now, you've noticed that I've got some buckets up there. And that's because energy is a scalar. Ooh, what does that mean? A scalar means it's not a vector. You don't have energy to the right or energy to the left or energy to the east or energy to the north. They're just energy. You got it or you don't got it. It's like money. Old guys got it. Young people don't. Okay? And like money or like paint that you either got or don't got, you can put it in a bucket. So I'm going to define a kinetic energy bucket. I'm going to define a gravitational potential energy bucket. And then I'm going to define a bucket that is the sum of those two. Now that third bucket we sometimes call total energy. Sometimes we call it mechanical energy. Its proper name is total mechanical energy. But we're going to be fairly sloppy. We're just going to call it total energy for the most part. Okay? Now, let's look at that first bucket, the kinetic energy bucket. This is the formula that fills that bucket. Trust me. Why would I lie? Okay? Now let me see if I can motivate it. Remember, energy is the capacity to do damage. When my daughter, bless her heart, was a teenager, I taught her how to drive in a 1979 Chrysler Cordova with rich Corinthian leather. Those of you that are not familiar with this car, it's a land yacht. The hood goes on forever. It's like a tank. And so my daughter was going around town with a large capacity to do damage. And we had a lot of problems with our insurance. But this wasn't the problem. This was. It turns out that my daughter only knew one way to drive that big old tank, and that was pedal to the metal. And that speed, that V, is squared. That means you're going twice as fast. There's 4 times the capacity to do damage. 3 times as fast, 3 times the capacity to do damage. I shouldn't share this. She's a wonderful, wonderful person. She's got 4 lovely children. One of the smartest people I know, a biologist. Excellent person. But I got to tell you this story. The church parking lot is empty except for 2 cars. Okay? My car and the person that I'm in the church talking to. And the next thing I know, my daughter's at the door knocking, and she said, "Dad, could you come out here?" So just tell me. No, come out here. She had been trying to teach her friend how to parallel park using this other guy's car as a prop. And during the process, she had completely taken out the side of his car. And I had to go back in and tell him that his car was totaled. Another time, I'm giving a lecture. I look up, and there are my 2 oldest children in the back. Just came to lecture. And so I was so proud that they would use their day off. It was a PIR day, and they used their day off to come to my lecture. I was just so touched. And so I involved them in the demos and everything, and it was a wonderful lecture. At the end, I said, "How did you like it?" "Oh, Dad, we got to talk." "What about it?" "Oh, Dad, we were on our way to a party, and Heidi was driving, and she sideswiped this car right near campus. We came to find you, but you were already teaching this lecture, so we had to sit through the whole thing." That is so crushed. Anyway, 1/2 mv squared. Memorize it. Those stories won't be on the exam. Okay, if we take m to be 1 kilogram, and it's not moving initially, then there's nothing in that bucket. Let's look at the second bucket, this gravitational bucket. Now, the formula for that bucket is mgh. Take my word for it. Now let me see if I can motivate that. If I remind you that energy is the capacity to do damage, whoa. Worried?
Yeah, a little bit.
A little bit. And he would be more worried if this were an anvil, okay? And he would be more worried if the anvil was higher above his head. Now, we've dealt with this. The bigger the mass, the more worried he'd be. The higher it is above his head, the more worried. What about that one there? Why is that in the equation?
Acceleration due to gravity.
Yeah. And what if we were on the moon? If I had that up above his head and I dropped it on the moon, would he be as afraid? No, because it would just gently float down. The acceleration due to gravity is 1/6 as strong on the moon as it is here. And so all of those things tell me how afraid I should be of something over my head. Now, I know that this is 1 kilogram for the ball. G is 9.8, we're going to call it 10 newtons for each kilogram. It's this H that we need to deal with. And that H requires a coordinate system. Now, when you wake up in the morning, you have a right to choose your own coordinate system. But there are some coordinate systems that are easier to use than others. If you always use the lowest point in your problem as your zero of height, you will never have negative height. And that'll simplify your problems. So I'm going to set up a coordinate system where that ball starts at 5 meters above the floor. And that's going to give me 10 times 5 or 50 units of energy. Does anyone know what the units of energy are? Joules, yes, joules, because energy is so valuable. Is that right?
No.
Maybe not? No, actually it's joules. We defined that unit to honor a dead professor, one of the best things you can do with your life. And let me put that one up here. Potential energy, gravitational, MGH. So we would have 50 joules of potential energy, and hence 50 joules of total energy. And then I drop the ball. Now once it gets down 1 meter, I look again and see how much are in each of the buckets. Now to figure out how much is in the kinetic energy bucket, I need to know how fast that ball is traveling. You've been able to solve that since the second week of class. We define a coordinate system. Let's call down the positive y direction. We set up our 5 players. My delta y in this coordinate system is a +1 meter. It starts from rest. The acceleration in this coordinate system is positive because it's down. I'm looking for v final after it's dropped 1 meter. Time is the one that I don't care about. That suggests I should use the equation that doesn't have time. I plug into it, and what I get is that. If delta y is equal to 1 meter, that gives me the square root of 20, which is 4.5. So let's fill up our buckets. The kinetic energy bucket is going to be 1/2 times 1 times the square root of 20 squared. And that's going to give me 10 units of kinetic energy. My potential energy, my height is only 4 meters now, so I now have 40 units, or 40 joules. And behold, that's what conservation means. When we say energy is conserved, what we mean is total mechanical energy is conserved, stays the same. Okay? Now, anytime something's conserved, you can use that. Those are some of the most powerful principles of physics, or places where something is conserved or stays the same. Now, let's let that ball drop another meter. Okay? Its speed is going to be the square root of 40, or 6.3. Okay? Well, let's see if that works out. Well, I know that the potential energy is 30 units, because it's 3 meters high. If that total energy stays 50, that means I must have 20 units of kinetic energy. Well, let's check. If I plug in, sure enough, I get 20. Now, what this gives me is a new way to answer this question. How fast will the ball be traveling when it's 1 meter from the ground? Well, I say the total energy still has to be 50 joules. That's what I started with. The gravitational energy when it's 1 meter above the ground is only 10 joules. That means I must have 40 joules in that kinetic energy bucket. If I know how much kinetic energy I have, and I know the mass of the ball, I can find the speed. I just plug and chug. What I get is 8.9. Now, I think I know what you're thinking right now. You're thinking, Greg, you just gave me a second way to solve a problem I didn't care about. I didn't care how fast that ball was going when it was 1 meter above the ground. I had to learn the first way to get through the first exam, and now you're teaching me a second way. Why don't I just use the first way? Well, it turns out that there are some problems that you cannot solve using the kinematic equations, and energy will allow us to solve those problems. There are other problems that you can solve both ways, with the kinematic equations or with energy. And in each of those cases, energy is going to be the easier way to go. Now, folks, I swear, got a building full of physicists. Well, there's some engineers on the third floor, but we ignore them. All these physicists, if they get a brand new problem they've never seen before, the first thing they try, the first thing they use is energy. Because if they can use energy to solve the problem, it's going to be easy. It's going to be easy. Okay? Now, here's a problem that's a little bit more challenging. I call it the Dukes of Hazzard problem. Now, you remember the Dukes of Hazzard TV show from back when I was alive. In every episode, they started with a brand new car. And for some reason I could never figure out, the doors would not open. So they had to slide in through the windows. And then during the episode, they were chased by the local cops. They had all sorts of fun. And before the end, they always destroyed that car. And then the next episode, they started with a new one. Now, it turns out that everything I know about the Dukes of Hazzard show, I heard from friends. Because my mother, bless her heart, would not allow my brothers and I to watch the show. It wasn't the violence, it wasn't the careless driving. What was it that my mom didn't like?
Daisy Dukes?
Daisy. Yeah, Daisy didn't dress right according to my mom. And so we could not watch the show. Okay, so here's the Dukes of Hazzard problem. They're going along at about 40 miles an hour, 20 meters per second. They go up this ramp, they launch themselves, yee-haw! And then they come crashing down, end of the episode. Now the question is, how fast are they going right before they crash? I have a question. Could we have solved this Dukes of Hazzard problem last week without the idea of energy? Just using what we knew with kinematics and dynamics? Yes or no? Could we have solved this problem? Okay. Some of us are still on spring break. The answer is yes. Okay? Let's talk about it. We know the initial velocity. If we draw a free body diagram for the car while it's on the ramp, we can break that free body diagram up into the x part and the y part with a coordinate system that's rotated to line up with the ramp. We can use, then, Newton's second law to figure out the acceleration of the car which would be down the ramp. Knowing this length, because we know that's 37 degrees and we know that's 5 meters, knowing this length, we could use the kinematic equations to figure out how fast the car's going at the top. That will give us the launch speed. Once we know how fast they launch and what angle they launch, it becomes a projectile motion problem. We would take that launch velocity, we would break up the x part and the y part. Why? Because nature treats those two differently. We would take the x part and leave it alone. The y part, we would add 10 meters per second. Every second that it flies through the air, we would add 10 meters per second down. And then, right before it lands, we would take the x part of the velocity that hadn't changed, the new y part of the velocity that we had calculated, we'd put them back together with Pythagorean theorem and get our answer. And that would take about 40 minutes. That would be hard. Let's do it with energy. With energy, we just fill up the buckets. Initially, that car has some kinetic energy because it's moving. It has some gravitational energy because it's up off the floor. And that's going to give me some total energy. Well, let's figure out how much energy. If I plug into those formulas, the kinetic energy, 1/2 mv squared, trust me, that's just going to be 1/2 times 1,000 kilograms, that's the mass of the car, times the speed, squared. Now 20 squared is 400, half of 400 is 200, 200 times 1,000 is 200,000 joules. Think of this as money, 200 grand. Now the gravitational energy, mgh, trust me, is going to be 1,000 kilograms. G is 9.8, let's call it 10 newtons for each kilogram. And the height, if you take my suggestion and choose the lowest point in the problem as your zero of height, if that's 15 and that's 5, they start 10 meters above our zero. And that's going to give me 10 times 10 times 1,000 or 100 grand. Now look at these units. The kilograms cancel, and what I'm left is a newton times a meter. A newton meter. Say that real fast 10 times. Newton meter, Newton meter, Newton meter, Newton meter, Newton meter. Yeah. And that's why we decided to call it a joule. Okay, that's going to be 10,000 joules. But it's just a newton times a meter. Okay? Now that means that the total energy is 300,000 joules. Now if that total energy is conserved, and let's assume for a moment that it is, we'll come back to that point. When it's at the top of the ramp, it has more gravitational energy than it started with, meaning it has less kinetic energy. But most importantly, right before it lands, if we conserve total energy, I've got 300,000 joules in that bucket. Right before the bumper hits the ground, the height of that car is 0. That means all of the energy has to be kinetic. Now I can solve my problem just trivially by saying the final kinetic energy right before it lands is 1/2 times the mass times the speed final squared. If this is 300,000 joules and the mass is 1,000 kilograms, I can solve for that V final. I multiply both sides by 2, I get 600,000, divide by 1,000, and I get 600 is equal to V final squared, or V final is equal to about 24.7 meters per second. Now folks, that was easy. That was a whole lot easier than the old way. And I hope that that when you get something for nothing, there's always a catch. There's always something that they're not telling you. Now, what information would we have gotten out of the old style solution, the hard way, that we don't get from this newfangled energy solution? What is missing? Raise your hand, please, to share, so that I can find you. Yes, sir.
Distance traveled in the X.
I'm sorry?
Distance traveled in the X.
Yeah, we have no idea how far they got from the edge of the cliff. What else?
The angle of the block.
Yes, because energy is a scalar, we will never learn anything about the direction they're heading right before they land, or anywhere else. We only get the speed, not the velocity. What else? The time in the air. This one is fundamental. You've all heard of the Heisenberg uncertainty principle, that when you're looking at things at a microscopic, in the quantum realm, that you can't know the position and the momentum of something completely. The momentum we're going to talk about in a week and a half. Well, there's a corollary to that, and that is that in that quantum realm, you can't learn anything. You can't know both the energy and the time completely. Now, in a macroscopic problem, what we find is that we can never learn anything about the time using an energy approach. It's lost. We also don't learn how high they go. We also don't learn anything about what happens in between. In other words, this part is not important. All that we care about is the initial state and the final state, and you get to decide what you mean by initial and final. Typically, you choose one of those states to be a time when you know everything about the motion. You choose the other one to be a time when you're looking for information. And what happens in between just doesn't matter. These guys could do a triple flip with a twist. It doesn't matter to the energy approach. Okay, check that your neighbor's on the bus with that. Now let's go back and talk about this assumption that the total energy was conserved. How many of you have been told in an earlier class that energy is always conserved? I was taught that. And that is true in the universe. Okay? Total energy, if you include all the different kinds of energy in the universe, is constant. And yet the energy in your house is not constant. That was what your dad was trying to get across. If you leave the door open or the windows open, the energy in your house does not stay conserved. Now, what I like to say is energy is always conserved, except when it's not, and it's usually not. Okay? In this case, in order to assume that the energy stayed the same, we had to ignore air resistance, that the air was not slowing down the car. We had to ignore any friction in the system that was turning kinetic energy into thermal energy. We had to make all sorts of assumptions to make that simplification that energy was conserved. Let's look at this demo here. When I was doing this demo over in Reed Hall, when it was attached to the ceiling, I would put this up against my nose, let it go, and it would literally come back and touch my nose. It was one of the funnest demos to do. Now, if you'll notice here, it comes back, it's nowhere close to hitting my nose. What's the difference? Why is it different over here than it was in Reed Hall?
Energy's lost moving the...
Oh, raise your hand. Yes.
Energy's lost moving the...
Yeah, it's lost. This gentleman, what's your name?
Garrett?
What he's saying is that, watch that bar up there. And it's just wiggling all over the place. And that is energy. That's energy that's lost to the bowling ball. Okay? Now in the Reed Hall, it was attached to the ceiling, which was attached to the walls, which was attached to the ground, which was attached to the earth. And so there was nothing wiggling up there. And so the energy was pretty much conserved. I mean, there's still the air resistance, but that wasn't much. Okay? Here, because of that wobbling that goes on, we lose a lot of energy. Now, we can still make some assumptions. If most of the energy is conserved, I could use energy to figure out how fast the ball is going at the lowest point of its swing. Remember, that was one of the questions that was asked during the video. How fast is it going at the lowest point in the swing? Answer this question. The acceleration of the bowling ball of death is constant as it swings back and forth. True or false? True or false? Okay. What I should have asked is it false or way false? Way false. You had a homework problem where you had a bowling ball of death, but actually it was a kid on a tire swing. But if it were a bowling ball of death, it would have been the same problem. We found that acceleration vector changed its magnitude, how big it is, and also its direction. Here, the bowling ball is speeding up and changing direction, turning. Here, it's slowing down and turning. Here, it's just turning. Here, it's just speeding up. Here, it's just slowing down. Now, why is that important? Because the old style approach to these problems relied on the kinematic equations on page 21 of your textbook. But if you look at those four equations on page 21, there's great big yellow caution tape around them. Danger, danger. Don't even think of using these equations unless what? Unless acceleration is constant. And so there are some problems that you can solve both ways. They will be easier with the energy approach. But there are other problems like this one here. If I were to ask you how fast is the ball going at the bottom of the swing, that would be trivial using energy. You would not be allowed to use the kinematic equations. They are not valid because the acceleration is not constant. Okay? Now, a word about this week's tutorial. It's not really a tutorial. Okay? A true tutorial is supposed to push you up against your misconceptions. It's supposed to make you feel uncomfortable. It's supposed to make you cry. And I'm here to tell you that the original tutorial on energy was a thing of beauty. The first tutorial that came out of Lillian McDermott's group on energy was the best of all the tutorials. I know because I wrote it. And it took her about 30 seconds after I left Seattle to junk it, to throw it out of the book. And I was offended. I was offended. And when I got here, I kept using it because it was the most beautiful of all the tutorials. And I used it for many years until my wife took the class just for fun. I still remember that day when she came home from tutorial. She was so mad. What were you thinking? Oh, she laid into me. And that's when I decided that my beautiful tutorial had to go. And so we sat down and we wrote what's not a tutorial, but just a worksheet. All you're going to do is you're going to work out some problems. Some of those problems you could have done the old-fashioned way. Some of them you couldn't do the old-fashioned way. But it's just going to walk you through the solution using energy. There's going to be no tears. There's going to be no bouncing up against your misconception. It's just going to be practice. I'm so sorry. I apologize. But that's the way it is. Okay. Let's look at this problem. One of your homework problems, problem 4. In this problem, we have a gymnast that is doing one of these grand loop-de-loops. And as he goes around, he pauses at the top for dramatic effect and then comes zipping down, and we want to know how fast he's going when he gets to the bottom. Now, the first question we ask is, can we use those kinematic equations on page 21? No or heck no? Heck no. The acceleration's not constant at all. So we have to use energy. And in this case, we're going to assume that energy is conserved. Now, what goes into that assumption? Well, where might energy be lost in this system? Friction with the hand. So one way we could get rid of that friction is we could put that white powder on the baby powder on his hand. And then we have to assume that this gymnast has a very, very strong grip. Because you imagine doing a loopy-loop like that with baby powder on your hand. I know that I'd just end up falling on the ground. So he's got to be able to hold that position really hard.
No air resistance.
And air resistance, we're going to have to ignore air resistance as well. But if we do that, we can solve this problem. If we assume that the energy lost in the friction or through the air resistance is small, then we can solve this problem. Now, the initial energy is gravitational. He's not moving up there, so it's not kinetic. Now, what is the height? Well, that depends on our coordinate system. Now, typically we choose the lowest point in the problem as our zero in height. But when you're dealing with a human, well, my head's at a different height than my feet. I'm messy. And so what we're going to do is we're going to model that human. We're going to find later in the tutorial that we can do this. We're going to model the human as if all of the mass is located right at the center of mass. And the center of mass for a human your age is about 2 inches behind your belly button. For a human my age, it's about 8 or 10 inches behind the belly button. You'll get there. Don't worry. Okay? So what we're going to do is we're going to choose our zero of height at the location of his belly button when he's at the lowest position. Now we're told that the distance between his belly button and his hand outstretched is 0.9 meters. And that means his initial position for his center of mass, his belly button, is 1.8 meters above our zero. Now, when he gets down here, because of my choice of zero height, he has no potential energy there. He has only kinetic energy. Now, you'll notice in this problem, if you've read it, that we don't give the mass of the gymnast. And this frustrates some people. Well, how do I find the kinetic energy without the mass? How do I find the potential energy without the mass? Well, the key is, when I set those two equal to each other, both sides have mass in them, and I can cancel out the mass. That is the most important principle at Disney World. Okay? When you have a roller coaster where all the energy is either gravitational or kinetic, that mass is going to cancel out. What that means is that everyone's going to get to the end of the ride at the same time. That's important. You don't want to leave the heavy guys behind. We all get down to the bottom of the roller coaster together because the mass cancels out. So now it just becomes plug and chug. Now, folks, this next exam, that involves energy is one in which I have typically every semester lots of high scores and lots of very low scores. And I wish I could say it was people that understand energy and those that don't understand energy, but that's not what it is. What it turns out to be is those that can do algebra and those that can't do algebra. It turns out that when you do energy problems, they very quickly turn into an algebra problem with one unknown. And you just solve for that unknown. That's why it's not my favorite thing to teach. It's like teaching math, and who would choose that voluntarily? That's silly. Okay, I hope I haven't offended anyone. But what I'm saying is that if algebra in particular is not your strong suit, it is time to practice. It is time to brush up on those skills, because that's what you will be doing on that third midterm. A lot of algebra. Okay? Now folks, we still have 5 minutes left, but unfortunately we've run out of lectures. So I'll let you go early. We'll give you a rebate in the mail. Check your mail, it'll be coming.